We're moving on to 370b. It's more about logarithms. So yesterday we talked about converting logarithms into exponential form and converting exponential form into logarithms. Today we're going to talk more about some of the other properties of logarithms. So if you turn to page 370, we're going to be doing 55 to 83 odd. So take a look at, we'll do 56 first. So it says, state the domain of the logarithm function in interval notation. So we're going to start off with log base 2 of 4x minus 1. What numbers are we not allowed to plug in? Well, if we look at regular logarithms, let's say I just had something simple, log base 10 of x. Okay, so if I set that equal to y, then I convert to exponent, and I get 10 to the y equals x. So y could be any number. It could be a natural number, it could be a fraction, it could be negative, it could be any real number. But if you're raising 10 to any real number, what sort of number would be the output? It's got to be positive. Could it be 0? No, there is no way to multiply 10s together and get a 0. Could it be 1? Yes, 10 to the 0 is 1. Could it be a fraction like 1/10? 10 to what power is 1/10? Negative 1. Could it be 1 over 100? 10 to the negative 2 is 100. So we know that the stuff on the inside here has to be positive. And we say positive, strictly positive, meaning 0 doesn't count. So the graph of a logarithm often looks like this. Or it could also be the other way. And you can see that it has a vertical asymptote at 0, and then none of the negative numbers appear. If you look back at number 56, this 2 doesn't really matter. It could be log base 10, log base 80. Technically there's no negative log bases. I guess you could make it up, but nobody really does. All I really care about is that this stuff on the inside is positive, or in other words, greater than 0. So 4x minus 1 has to be strictly greater than 0, not equal to. So I add 1, and I get 4x is greater than 1, divide by 4, x is greater than 1/4. How do I write that in interval notation? So from 1/4 to infinity, and what symbols does it get on the edges? Parentheses on the left, because this is not equal to, and infinity always gets a parenthesis. So that would be from 1/4 to infinity. Okay, look at number 60. 3 minus x has to be greater than 0. How do we solve that? So we could subtract 3. Negative x is greater than negative 3. Divide by negative 1, which flips the inequality. X is less than 3. Or the easier way would have been just add x to the other side. So 3 is greater than x. What is that in interval notation? So we have to list the small end first, negative infinity to 3. And they're both parentheses. Okay, look at 64. 1 minus x squared is greater than or equal to 0. I'm going to add x squared. 1 is greater than x squared. Take the square root. And I get x is less than 1, and x is not less than, greater than negative 1. So what is the interval that demonstrates less than 1 and greater than negative 1? From negative 1 to 1. Now I want to point something out. Right here we have x squared less than 1. A less than squared, or this is also true of absolute values, they create what is called an AND situation. You're going to get two endpoints of your answers, and the correct solution is between both of them. It's AND. It has to be less than one and greater than the other. So less than this one and greater than the other. If it would have been the other way around, x squared is greater than 1, greater than symbols, when you have two answers, are OR equations. So this would be x is greater than 1 or x is less than negative 1, in which case your answers look like this. It's going to be this way and this way. So if you have a double answer equation and it says x squared less than, that's an and they're going to point toward the middle. So this one right here, we have negative 1 and 1, and it's everything in between. But if it's a greater than, then it's an OR, and you fill one end or the other. Does that make sense? Okay, so let's look at '62. So x plus 1, the absolute value of x plus 1, has to be greater than 0. Is this an AND or an OR? Less than is an AND, greater than is an OR. So this is x plus 1 is greater than 0, and x plus 1 is less than negative 0, but it just ends up being 0. So we get x is greater than negative 1. X is less, uh-oh. Man, why does this always happen to me? Greater than, that one ended up being an AND. Oh, that one ended up being an AND because it's a 0. If it would have been like 6, then it would have gone in the other direction, but because 0 works. So does this make any sense? Well, if we plug in negative 1, we get negative 1 and we get a 0, which the log base 2 of 0 of 1 of log base 2 of 0 doesn't really exist. Right? So it's got to be this one. Hold on. That's going to confuse you. Let me do that a different way. So take a look at 61. Sorry, I didn't explain that very well. So the absolute value of x has to be greater than 0. So we end up with x is greater than 0 and x is less than, it should be negative 0, but it ends up just being 0. Okay? So this says everything bigger than 0 and everything smaller than 0. So essentially, it's from negative infinity to 0 and from 0 to infinity. Right? So if I plug in negative 5, am I okay? I stick a negative 5 in the absolute value and that kills the negative. Can you take the log of 5? Yes. So what about 3? The absolute value of 3 is 3, and you can take the log of 3, that's okay, but I can't plug in 0. Because if you stick in 0, the absolute value of 0 is 0, and you can't take the log of 0. On that graph, there's a vertical asymptote at 0, and you're not allowed to plug it in. Okay, so what about 66? Actually, we'll do 65. So in 65, 10 plus 3x minus x squared has to be greater than 0. I would move everything to the other side, to the right side. So 0 is greater than x squared minus 10x minus, 3x minus 10. Does that factor? So x minus 5 and x plus 2. So my critical points here are going to be at 5 and at negative 2. And now we just need to decide, is it going to be between those two, or is it going to be outside of those two? So on my number line, negative 2 and 5, and I know that these are not equal. Is it everything in the middle, or is it everything on the edges? What's the easiest way to tell? What do you mean? Well, it's the trouble is you can't subtract this until you do the multiplication. There may be a way to do that, but I'm not sure how to do it. I like Chim's idea. Just pick one. Pick a number. What number is going to be easiest? Nope. 0. If I put 0 in here, that goes away, and that goes away. Is 10 bigger than 0? So if that works, everything in between should work, and the outside stuff should not work. So if I put in 6, it shouldn't work. 10 plus 18 minus 36, is that bigger than 0? No. If I plugged in negative 3, 10 minus 9 minus, well, it's going to be minus 9. Is that bigger than 0? No. So none of this stuff works, and none of this stuff works, so the answer is in the middle. So that would be from negative 2 to 5. Does that make sense? So you're just going to set it greater than or equal to 0, find the endpoints, if there are 2 of them, and then just figure out which is which. Take a look at 63, though. What should we do with 63? You could subtract 1 in square root, or you're going to get i's. You could factor into x plus I and x minus I. When is x squared plus 1 not greater than 0? So x squared plus 1 greater than 0. What is the smallest that x squared can ever be? 0. 0 times 0 is 0. If you plug in 1, 1 squared is 1, and now I'm bigger than 0. If I plug in negative 1, negative 1 squared is also 1, which is still bigger than 0. So x squared can be as small as 0. And 0 plus 1 is always bigger than 0. So this one is actually all real numbers. There is no number I'm not allowed to plug in, because there is no way this quadratic misses the x-axis. Right? If I graph that, it misses the x-axis, which means it has no roots and it's never negative. So because this graph is always positive, this graph will always exist on every x value. Okay. So, take a look at 68. Well, I guess. So, a regular logarithm graph looks like this. Okay? Now that's log base A of x. And that is the exact inverse of this graph, where this is b times m to the x. So let's say this was the graph of 2 to the x, y equals 2 to the x. Then the inverse graph is going to be log base 2 of x. Okay? But not all exponential graphs look like this. If the base is less than 1, what does it look like? What's the opposite of exponential growth? Exponential decay, which looks like this. So that would be like 0.5 to the x. So this is exponential decay, and the inverse of that is logarithmic decay, which would be like this. Yeah, it's kind of a mess. So if your base is greater than 1, then your exponent is going to be growing. And remember, everything is reflecting across this line. So my exponential growth, where my base is bigger than 1, mirrors my logarithm equation, where my base is bigger than 1. And my exponential decay, where my base is less than 1, is a mirror image of my logarithmic decay, where my base is less than 1. So this would be like log base 0.5 of x. And then the only other thing you have to worry about is reflections. If you change the sign on x, that means all of the x-axis values flip around, and that's a y-axis reflection. If you change the sign on the logarithm, that changes all the y values, and it flips vertically. So number 68 is an exponential growth equation, like this, that gets turned into a logarithm equation that looks like that, and then the x's reflect, so every x value is going to move to the other side, so it would be a graph that looks like this. Okay, so that would be number B? No. D. E. What did you guys say, D or E? E. Okay, look at 72. So 72, essentially, we take a 5 to the x equation, all right, and we're going to reflect it across the x-axis. Oh, we're going to turn it into a logarithm. So we turn it into a logarithm, we reflect it across the x-axis, and then we move it 3 horizontally, and then we flip it across the y-axis, and then we add 2. Now it's getting kind of complicated, right? There's got to be a way to do this in my calculator. What's the problem about graphing that? It's not a log base 10. Now, technically it's not going to matter much because a log base 10 and a log base 5 are just going to vary in steepness. But what you need to do is do the change of base, negative ln of 3 minus x over the ln of 5, and then add 2 on the outside. So that same change of base formula that we used yesterday, you can use it today. We don't have a log base 5 button. I guess some of you do. You could go into math and type it in that way. But I don't ever use that. So we go into y equals, so negative natural log of 3 minus x divided by the natural log of 5 and then add 2, and that will do all the transformations for you. My calculator gave up, but it's going to continue. It's going to have a vertical asymptote at x equals 3. Okay, and does that take us all the way to the end? Oh. Yeah, so 73 through 83, you're just going to graph it and describe the transformation. So For instance, 73 goes right 1, 75 goes left 2, and then you can graph it on your calculator. All right? Good luck.